Welcome to this video. In this video, I want to tell you more about equivalent circuits. So if we have a coil such as the one shown here, often we want to somehow represent that we are putting this coil into our system, into our circuit by placing an equivalent circuit on our graphical representation. So typically, if you see a circuit diagram, it doesn't show a picture of a coil, but it shows some representation of how it's behaving. And in this video, I'm going to talk about how such an equivalent circuit is set up and what it means then in the end also. Okay, let's get started. So the idea behind an equivalent circuit is that we want to describe the behavior of the physical system with basic circuit elements. So we don't want to put pictures of our coil into a circuit, but we want to describe how it's behaving. And these equivalent circuits are useful because they give you insights into the considered effects, and they also are suitable for deriving a mathematical model of what's happening in the circuit for the analysis and for the design of the circuit. If we are doing an equivalent circuit, that means, first of all, that we are typically doing a lumped model. So what is a lumped model? Consider we have a conductor as shown here. So we have a conductor of a certain length. This conductor has a length, a certain diameter, and a certain resistivity depending on, or conductivity depending on the material that we have. So if we want to exactly describe what's happening in the conductor, we need to calculate what the electric field is across the conductor to describe how it is behaving along the full length. Often, particularly if we are operating at low frequencies, we can actually represent such a conductor quite well by just using such a discrete ohmic resistance here, so just a single resistor. And that is what is meant by doing an equivalent circuit. We don't show the photograph of the conductor in the circuit plan, but we just show a resistor. And that doesn't mean that the resistor is happening just somewhere in the middle here. It is just a representation, a lumped representation of the overall behavior of this conductor here. So the conductor has resistive effects along the whole length, but in the lumped model, we just put it in one discrete element. This is typically working out quite well if you're at low frequencies. If you're going to higher frequencies, at some point you have to consider transmission line effects along conductors, for example. And for that, you have to think of more sophisticated equivalent circuits. For low frequencies, on the other hand, we often can do this simple representation. If we do this simple representation and we look at this line here, it means that this line is ideally conductive. So what we read from this equivalent circuit is all the resistivity is in this lumped element, and all the other lines that are shown are ideally conductive, so they are considered to not have any resistance at all and to be all along the line at the same electric potential. So there is no electric field along this line that is shown in an equivalent circuit. All the resistive effects are combined into the lumped element. So the basic circuit elements that are used for deriving equivalent circuits are these three here. We have already just seen the ohmic resistor that combines the resistive effects into one discrete element. Then we have here the inductance as the second element. That is what we were just looking at in a previous video already. So this is the image here for what a circuit element inductance looks like. So in Germany, at least, we draw it like this. And the voltage that is observed across the inductor is given by UL as L, the inductance, times the time derivative of the current. That defines what the voltage across an inductor is. And then as the third basic element for equivalent circuits, we have the capacitance here. And the capacitance relates capacitive or energy storage effects to the equation given here. So the current I through a capacitor is given by capacitance C times the derivative of the voltage. So if we are in the static case, that is, we don't have any change, or the stationary case actually as well, if we don't have any change of the voltage over time, then that means we don't have any current through the conductor. If the voltage is changing over time, that means we are charging or discharging the capacitor. That is, we are increasing the electric field or decreasing the electric field stored in these capacitive effects. Then that means we have a charging or discharging current flowing also. So these three basic circuit elements are typically used in order to describe how a certain component behaves. All these equations here are now given in the time domain. In electrical engineering, we typically work in the frequency domain. So for completeness, here are also the frequency domain equations given now. So in the frequency domain, we use the complex notation, and we write here the complex current as I, that with the underlined, and with the hat, the I hat is the amplitude of the current I in the complex plane. And this equation in the time domain just converts to the same equation in the frequency domain. If we go with the derivative equation from the time domain to the frequency domain, then we get, instead of the derivative, a multiplication with j omega, where j is the square root of -1, the complex number, and omega is 2 pi times the frequency. So this equation in the time domain becomes this equation in the frequency domain. And then for the capacitance, we also have a derivative. So the time domain equation again goes to an equation with a j omega multiplication in order to go to the frequency domain. If we do the evaluation of how components behave under different frequencies, typically it's a lot easier to calculate it in the frequency domain, and that's why this is one of the important techniques in electrical engineering, to use these frequency domain representations and calculations. So let's consider an example of a coil, and this coil that I'm showing you here is a charging coil that is wound in a single layer. So it's on a plane. We have the wound coil here, and if we want to describe this coil now as an equivalent circuit, of course, first of all, we have to consider the inductive effects. So the inductive effects need to be put into the equivalent circuit here, looking at this inductor. And also we have, in a simple model, we should consider the resistive effects of the coil due to the wire itself, and how high the resistance is will depend on the length and the diameter and the material of the wire. So the resistive effects of this wire are put into this series resistor that is shown here. And if we now write down the impedance of this equivalent circuit, we find that this element has ohmic inductive behavior given by an impedance Z in the complex plane, that is in the frequency domain, by series resistance plus j omega L for the inductive effects. And what we can see from this equation is if we change the frequency, then this omega, which is 2 pi times the frequency, will change. So the impedance of our coil will be frequency dependent always, and that is what is represented in this equation here. So such a coil in a simple model would be given by the representation as it is shown here. Also, we can see from this representation, if we are using this coil for a static, for a stationary current I, so no time change at a frequency of 0, that is, then that means this is just like a wire. So if we don't have any changes with time, we don't have any inductive effects, and the coil just behaves like a wire. And that is also given in this impedance equation down here. For omega equals 0, this part here goes to 0 or is 0, and then we only have the series resistance of the wire. So this model also includes the very low frequency case that we only have the wire resistance to consider. So this is a first simple model. But if you go to higher frequencies, we might actually need to consider other effects. And a bit more complex model of this coil would look like this. So we have two additional elements now here in this equivalent circuit. The first additional element is this capacitor C here. Why do we have a capacitor in a coil? We have capacitive effects between the wire loops. So if we have several wires, that means we have wires running next to each other that are separated by the insulator between the wires. If it wasn't with insulator, it would not work out. So you always need, if you wind a coil, you can just not take just a blank copper wire. It would all be connected electrically, but you need to have a copper wire that has an insulator around it. So what you see in this photograph here is will be wire that has an insulating layer such that the individual windings are electrically insulated. And then if you have a conductor, an insulator, and a conductor next to each other, that again means that you have a capacitive effect going on. And these capacitive effects between the wire loops are described by the capacitor C. So there is nowhere, if you see this circuit model, there is nowhere a capacitor soldered into this coil here, but it just describes the effects of the coil itself and the dielectric effects that are happening in the insulation between the wires. Then also you might have, for example, ohmic losses through the insulation. And so no insulation is really perfect, so there might be some loss actually where you have the current, some small current flowing through the insulation from one wire to the next in the radial direction. And that would mean you have a parallel resistive effect. And that is given by this parallel resistance down here. So this would be a more complete equivalent circuit model of such simple coil as the one shown here. If the impedance is calculated for this model, then you get the value given down here in the equation. So you have a parallel connection of these three different branches. Therefore, the overall impedance is 1 over the impedance of each of the elements in each of the branches. So we have in this branch here the series of the resistor and the inductor. So therefore we take 1 over the sum. In the second branch we have the capacitor. I actually put it down here in the third part. So for the capacitor we just have J omega C. And then we have in the third branch here the parallel resistance, and that is just 1 over R parallel. So that is the overall impedance then. So you might find as an equivalent circuit for such a coil this diagram here. And now hopefully you can see what it means or why this is the equivalent circuit of that. It just means that different effects are considered. Inductive effects, resistive effects, capacitive effects, they all occur in this coil here, and therefore they need to be considered to completely describe the behavior of the coil, or to do a good model of the behavior of the coil. One more important point on this, that is, you can also actually see, if you look at this equivalent circuit, you can see that you have a capacitor and you have an inductor. And thinking back to some basic electrical engineering, if you have a circuit with a capacitor and an inductor, this circuit can have a resonance. And the resonance occurs when the energy is resonating back and forth between the conductor and the capacitor. And so therefore, a certain frequency will exist where this phenomenon will happen in the case, and that is actually the resonance then of this coil. And you can calculate from this equation here where the resonance of the coil happens. It's typically, if you have small capacitive effects, it will typically be at high frequencies, and therefore for energy applications it is less important than for high frequency applications. But each coil also will have a resonant effect because of this parasitic capacitance here that we have due to the insulation between the inductors. So now you hopefully understand why a coil can also be considered as a resonant circuit, or is a resonant circuit. The resonant frequencies are just typically quite high. But what has to be considered always is that the impedance of a coil will be frequency dependent. So it will not be constant over all different frequencies. So summarizing this now, if you have a coil, and let's take this coil again, if you have a coil here and you want to put this into your circuit somehow, you have to think of what is a good representation of the coil that represents it well enough for whatever I want to do. And the answer to this will always depend on what actually is the geometry, what are the materials, what is the frequency of operation. So if the geometry is fixed with time, we don't have any nonlinear effects, and then first of all we can go ahead and describe the coil by an inductance L. Also then, if the frequency of operation is rather low, then it's often a good representation to neglect all capacitive effects and just put in the inductive effects. And finally, of course, the question is, what wire did you use? Is the wire resistance important or not? So the very simplest image of this inductor would be this equivalent circuit with just a coil. But often this is not sufficient, and you need to go to more sophisticated equivalent circuits, such as the one shown here, in order to really describe what the behavior of the coil is. All the equivalent circuits, they are lumped models, so they are approximations of the behavior of the coil. If you want to know, so what does it actually really exactly do, then you need to find the full field solution. So you take Maxwell's equations, you calculate exactly what is happening, and this can be done numerically, for example, using the finite element method. And then if you have calculated the full field solution, then you will know what exactly is happening for this coil and for the volume that is surrounding it, and that will be penetrated by a magnetic field caused by this coil. So the full field solution always gives you the exact solution, but the equivalent circuit representations are good for estimating what is happening, for approximating what is happening, and also for designing your systems. Thanks for watching.